Okay, so let's continue discussing the observations. Let me get my laser pointer. So here's a cartoon of this thing called the accretion disk, and we'll look at this mathematically in some simplified form. And we can think of it in a simplified way by imagining that, as we mentioned before, it's sort of like, so the structure is very thin. It's a disc-like flat structure, and so the further away we are, if we think of the solar system, you rotate slower than you do if you're closer in, where you rotate faster. Right? This is just basic principles of energy and angular momentum conservation, as we mentioned. And we can sort of think of the disk as being a structure that has enough material that material rotating at this radial distance from the central object, in this case, a black hole, sort of makes contact with material further out. The density is high enough. And so the faster moving material on a ring or an annulus closer in sort of transfers its energy to a ring that's further out. There's enough contact. That's not really the way this works. It works with magnetic fields. It's a very complicated process. But we can think of this in this way. It's very useful because it allows us to get a sense of how it is that these flattened structures have lots of their energy very close to the black hole. We're tapping into the gravitational potential well of the black hole. The closer you are in, the faster you're going, the more you will transfer that energy by making contact with annuli further and further out. You'll transfer that energy further out into this accretion disk. And so you can sort of calculate the brightness of the disk by thinking in terms of those ideas. So we'll look at some of the math. This thin disk model was developed in the 1970s, and this kind of structure where the energy is a sufficient amount of energy is lost so that you get a thin-like structure, a thin accretion disk model, is what's called, well, it's a very bright kind of disk, and it's called high excitation for that region. And we really talk about certain kinds of emission that you observe from the material that's rotating around the plasma. And you can tell from that emission what kind of material is in the disk. Another kind of structure that's, so we're thinking in terms of a couple simplified versions of sort of opposite scenarios. And one is the system is dense enough that it collides and overall flattens into this pancake-like structure, in a case where the density is not very high, so that you don't get these rings rubbing up against each other. You don't get enough friction. The structure sort of doesn't lose its energy, and so it doesn't flatten out into a disk. This is called an advection dominated accretion flow, where the stuff is falling in. It kind of holds on to its energy as it's advected inwards. And so this is what's called a low excitation, opposite to a high excitation. You don't see the bright emission lines characteristic of this kind of disk. We'll look into that a little bit as well. And these kinds of things are what theorists basically use to try to explain the observations. We'll do the same as we try to explain the observations. The rate at which this stuff can fall in is limited. It's called the Eddington limit, due to the fact that you generate energy. The energy actually has pressure, and so it pushes the material outward. So you can't just gravity is pulling in, and then there's this radiation pressure pushing outwards. And so if there's enough radiation pressure, it'll stop the inward migration due to gravity. So let's think a little bit about how jets and disks are connected, and see if the observations give us some hints as to what's going on. What are the combinations that occur in nature, so that we can say things like, oh, we can you get these kinds of jets with these kinds of disks. Is it a one-to-one kind of thing? And unfortunately, the situation is rather complicated. So we observe, as we mentioned before, these FR2 jetted systems. These are the most collimated, the most powerful jets observed in the universe. And they're surrounded by accretion disks that seem to be thin, the kind that we talked about before, where there's high excitation, you have these bright disks. And so it would be nice if for example, we look at the FR1s and we don't see very bright disks, then we could get a sense of the connection, why certain jets are forming with certain disks and so on. But unfortunately, we don't see that. So FR2s are not exclusively surrounded by bright disks. They seem to be also surrounded by these dull disks, these low excitation disks, these sort of puffed up structures that are not losing their energy very efficiently. And so it looks like at least for the FR2 jets, it's not the disk that determines the jet, right? It's not the kind of disk. So let's look at FR1 jets, and there we see that it's mostly these dull accretion disks. So that's somewhat interesting, and but it's actually not exclusive. So you actually do have some FR1 jets that are coming from very bright disks. And so what's the reason why we haven't seen these? And some decades ago, astronomers thought, okay, but these FR1 jets are a little bit less powerful. Maybe we're not seeing them. They're formed at earlier times. And we'll see them eventually. And it turns out that we've only seen just a few more FR1s with bright, thin disks, high excitation systems that are sort of modeled as these thin disks. And so to give you a sense here, we're talking about hundreds of thousands of objects, and we've only seen a handful of these FR1s with bright disks. So this is something that needs to be explained. And so we sort of summarize the most dominant subclasses of these active galaxies, as we mentioned, are jetless. And so we think of them as having thin disks, a number of these, and these are the high excitation ones. And most high excitation systems don't have jets, and we call them in different ways. And some of these things sort of overlap. But radio quiet quasars, radio indicates the jet. These are, the quasar term usually means that a lot of material is falling into them. And so these tend, we think, to form as a result of mergers, and mergers lead to elliptical kinds of structures, elliptical galaxies being formed. So all the energy gets remixed and they sort of puff up again. And then over time, they have to flatten out into spiral galaxies. But we also see radio quiet, or again, jetless, active galaxies. When you use the term AGN for radio quiet as opposed to quasar, it kind of suggests that the rate at which stuff is falling in is not as great as the quasars. And these can be both in ellipticals and in spirals. Of course, in spirals, we don't think of them as being the result of mergers, but there are processes that sort of funnel material into the center of the spiral galaxy, but it's not as dominant as you'd get from a merger. And so you'll get a bright disk, but it's not as bright as the ones in the ones formed as a result of mergers. Then there are these other objects that sort of overlap with radio quiet AGN. You kind of can intermix these two. They're called Seyfert 1 and 2s, but these are generally almost exclusively, I think, spiral galaxies. And then there's the narrow line Seyfert 1s, which are sort of a subclass. And strangely, some of these have found to have jets. So we have to explain jets in spiral galaxies as well. People were thinking, oh, okay, it's clear that the jets can form only as a result of mergers. Now you see actually powerful jets in spiral galaxies. Of course, they're the minority there as well, and most narrow line Seyfert 1s don't have jets. So what's the reason why that occurs? And then there are other interesting properties in these narrow line Seyfert 1s that we'll discuss later on. And then there are the objects that don't have high excitation or thin disks, and they tend to be modeled as puffed up structures. And these may even have jets, but if they have them, they're kind of weak and compact, and they might be sort of late state evolution. These are found, I think, both in ellipticals as well as in spirals, and all of this needs to be explained. And so we'll continue with the observations for a little bit longer.